To motivate our work with polynomials, here are some questions involving integer division. Part A, use long division to find the quotient and remainder when dividing 5,273 by 6. Part B, based on your work in Part A, fill in the blanks. 5273 equals 6 times blank plus blank. And Part C, how do you know that you found the correct remainder in the division above? So please pause the video and work on these 3 questions, and we'll go over them shortly. Now, the answer to Part A can be found in Chapter 29 of the textbook, so I'll leave it up to you to read it there. But let's move on to Part B. It turns out that 5273 is 6 times 878, that's the quotient, plus the remainder of 5. And how do we know that our remainder of 5 is correct? Well, because it's strictly less than 6, that's the number that we're trying to divide by, and also our remainder of 5 is non-negative. So it satisfies the requirements of the remainder. Once again, our remainder must be strictly less than 6, the number that we're trying to divide by, and also our remainder must be non-negative. Now let's try dividing a polynomial by another polynomial. So we have f of x and g of x with coefficients that are real numbers, and we have the long division set up for them. Now just some terminologies here. The polynomial that's getting divided, f of x, that's called the dividend. And the polynomial that's doing the dividing, in this case, g of x, or x squared plus 1, that's the divisor. The outcome of the division process is called a quotient, and then we'll get the remainder at the bottom. And so let's see what we can do. So we start, as we would do with integer long division, say how many times does x squared plus 1 go into 5x to the 4th? Well, that's going to be 5x squared, because 5x squared times x squared will be 5x to the 4th, which will cancel out that leading term. And so aligning the degrees, let's write down 5x squared right here. And then we'll multiply this by x squared plus 1. And so if we do that, we get 5x to the 4th plus 5x squared. And let's align the degrees once again. And then we subtract this from the original polynomial. So we'll put parentheses around it, subtract. Let's draw a horizontal line going across. And upon subtracting, the leading term cancels. And then we have x cubed minus 3x squared minus 5x squared. So that's minus 8x squared. And let's bring down the rest. Plus 4x minus 3. And then we repeat. So now, how many times does x squared plus 1 go into x cubed? Well, this will be plus x, because then when we multiply x times x squared, that'll give us x cubed here, and that's going to cancel out the leading term. And so upon multiplying, we get x cubed, and then plus x. And now we can subtract again. And so get a horizontal line once again. So the leading terms cancel each other out, and we have minus 8x squared, 4x minus x, so that's plus 3x. And then let's bring down the minus 3. And then we say, how many times does x squared plus 1 go into minus 8x squared plus etc.? Well, that'll be negative 8. And then we have minus 8x squared. And then minus 8. So let's line them up right here. And then we're going to subtract once more. Horizontal line. And then upon subtraction, the leading terms cancel, and we have 3x. And then we have negative 3 minus negative 8. So that would be negative 3 plus 8 or plus 5. And then we can't go on anymore because this remainder is less than our divisor in the sense of its degree. So the degree of our remainder is 1 because it's a linear polynomial. The degree of our divisor is 2 because it's a quadratic. And then we know we're done with the long division because the divisor no longer goes into what we have left. And so to summarize, our quotient is 5x squared plus x minus 8. And our remainder is 3x plus 5. And that's how we do long division with polynomials. We just used long division to divide f of x by g of x. And using that result, we can rewrite f of x as follows. F of x is equal to x squared plus 1, that's the divisor, times the quotient q of x, which was 5x squared plus x minus 8, but we'll just write it as q of x because that's not going to play a prominent role here, plus the remainder 3x plus 5. Now, I'll once again emphasize that the remainder must be strictly less than the divisor. That was the same when we were working with integers, and it's the same when we're working with polynomials. But because we're working with polynomials, what we really mean is that the degree of the remainder, in this case 3x plus 5, must be less than the degree of the divisor, x squared plus 1, which it is because our remainder has degree 1 and our divisor has degree 2. This example can be generalized by the following theorem. It's called the division algorithm, and we saw the division algorithm for the integers earlier in the course, and this is the polynomial version of that. The theorem states, let f of x and g of x be polynomials in f bracket x, where the coefficient ring f is a field. And so please take a look at chapter 29 in the textbook to see why it's important that the coefficients of our polynomials come from a field. But let us move on. We'll also assume that g of x is a non-zero polynomial because g of x is our divisor, and we can't divide by the zero polynomial. And the theorem states that there exists the quotient q of x and the remainder r of x such that f of x is g of x times q of x plus the remainder r of x, with an important restriction on the remainder polynomial r of x. Now, in a nutshell, we're saying that our remainder must be strictly less than our divisor. And more precisely, the theorem says that the remainder r of x has to be the zero polynomial, or that its degree must be less than the degree of the divisor. And the reason why we break this up into these two cases is because the zero polynomial has undefined degree. So we have to treat it separately and say, well, either the remainder is 0, or if it's not, then we can talk about its degree. Then its degree must be strictly less than the degree of the divisor. And so that's the essence of the division algorithm. Now please pause the video and work on day 29 classwork. And afterwards, we'll go over some of the problems and concepts. In the classwork today, we worked with the polynomial f of x equals 4x cubed minus 9x squared plus 5x minus 6 with coefficients that are real numbers. And we observed a couple of things about this polynomial. First, if we evaluate f of 2 by replacing x by 2, then we obtained 0. So f of 2 was equal to 0. And then we asked, well, what does that result tell us about the way our polynomial f of x factors? Well, it turns out that one of the factors of f of x is x minus 2. And then we can find the other factor, in this case 4x squared minus x plus 3, using long division. But the key thing here is that f of x has a factor x minus 2, and we also saw that f of 2 is equal to 0. And we'll discuss the connections between these two observations in the next slide. But before that, we'll introduce a terminology. Now, on one hand, we can say that f of x is a multiple of x minus 2. And that's what we have here. F of x is equal to x minus 2 times another polynomial with no remainder. Now, synonymously, we can say x minus 2 is a factor of f of x. And here's a shorthand for it. This literally means x minus 2 is a factor of f of x. Now, saying x minus 2 is a factor of f of x in the world of polynomials is analogous to saying 4 is a divisor of 24 in the world of integers. And we'll notice that the notation is essentially the same as well. Now here's our polynomial once again. And we saw that for this polynomial, f of 2 is equal to 0. And also x minus 2 is a factor of f of x. And here's a theorem that generalizes this example. It's called the factor theorem. Once again, the coefficients of our polynomials must come from a field. So we'll let capital F be a field, little a be an element of f. And so in our example, this is 2 being an element of the reals. And then f of x being our polynomial. Then the factor theorem says f of a is equal to 0 if and only if x minus a is a factor of f of x. Now this is an if and only if statement. So there are actually two statements we need to prove. First is if f of a is equal to 0, then x minus a is a factor of f of x. Then the second statement is its converse, namely if x minus a is a factor of f of x, then f of a is equal to 0. And as typical of these if and only if statements, one of those two happens to be more difficult than the other to prove. And it's the first one that's more difficult. So if we go back to our example, if f of 2 is equal to 0, then x minus 2 is a factor of f of x. This direction happens to be the harder one of the two. And then the other direction, namely, if x minus 2 is a factor of f of x, then f of 2 is equal to 0, that happens to be the easier direction of the two. And so we will focus on proving the harder direction in this lesson, and then I'll leave it up to you to read in chapter 29 of the textbook for the proof of the easier direction. For the harder direction of the factor theorem, we will need to prove that x minus 2, or more generally x minus a, is a factor of f of x. Now, before we do that, here is a proof know-how about how do we show that a polynomial g of x is a factor of f of x. And in a nutshell, we do this by trying to divide f of x by g of x, and then showing that the remainder must be 0. So more precisely, we would write f of x as g of x times the quotient q of x plus the remainder r of x using the division algorithm, where the remainder r of x is strictly less than the divisor g of x. And then try to show that the remainder must be 0. Because if we can do that, if this remainder is 0, then we're left with the relationship f of x is equal to g of x times q of x, and therefore g of x must be a factor of f of x. And so we will apply this proof know-how when proving the harder direction of the factor theorem in the next slide. We will now prove the harder direction of the factor theorem, which states let f be a field and a an element of f. So in our example, this was 2, that was a real number, and then a polynomial f of x in capital F bracket x. So the theorem states if f of a is 0, then x minus a is a factor of f of x. And so we've identified the hypothesis and the conclusion of this implication. So as usual, we've written down the first line, assuming f of a is 0, and our last line of the proof, our conclusion. Now, to show that x minus a is a factor of f of x, we will use the proof know-how from the previous slide. In other words, we'll try to divide f of x by x minus a, and then show that the remainder must be 0. So more precisely, we use the division algorithm and let f of x be x minus a times q of x plus r of x, where q of x is a quotient, r of x is the remainder polynomial, with a certain restriction on the remainder. Namely, it's either equal to the 0 polynomial or that its degree is less than the degree of the divisor x minus a. Now, x minus a is a linear polynomial, and that means its degree is equal to 1. In other words, r of x is either the 0 polynomial or a non-zero polynomial of degree less than 1, and hence a constant. So in either case, we can conclude that r of x is a constant polynomial, and therefore we can write f of x as x minus a times q of x plus r, where r is an element of the field f. Once again, because we can view r of x as a constant. Now, solving this equation for r, we get the following. And then we can substitute x equals a to find the value of r. So we get r is equal to f of a minus a times q of a. And here's where we use our hypothesis. F of a is 0, because now we can replace this f of a by 0. And then we have a minus a, which is 0, times whatever value q of a is. This whole expression ends up being 0. And therefore, r must be 0. And here's a key idea. Because r is a constant, its value is unaffected by the substitution x minus a. As opposed to, say, if you had a polynomial like x squared, and you plug in a value of 2, and you get 4. Well, we can't say the polynomial x squared is the same as 4. Whereas r being a constant, substituting any value in for x doesn't change its value. And that's why we can say r is equal to 0. And then since the remainder is 0, we can say that f of x is x minus a times q of x without any remainder. And so that's our second to last step. And therefore, x minus a is a factor of f of x. And that's the end of our proof and also the end of this lesson. So I will see you next time.